right, hello everyone. Welcome to the next part of this lecture. In the previous part, we kind of derived these expressions for a series RLC circuit and looking at the natural response of it. We kind of derived the expressions for the currents, and we also figured it out how to solve them in a kind of a stepwise way. So let's do this kind of an example problem, and things are going to become more clear. Again, here's a series RLC circuits, and we are interested in finding the natural response of that. The value of the capacitor is given 0.1 microfarad, inductor is given 100 millihenry, and the resistance is 560 ohms. It already says that the capacitor is charged to 100 volts, right? And then it says that at t is equal to 0, the capacitor is discharged. As you can see, there is no DC source shown here. So, but it provides you this indication that the capacitor was charged to 100 volts. So this means that it was charged to 100 volts by some DC source, right? So assume that in this circuit, we are at t is equal to 0, we are bringing in a charged capacitor to this circuit where inductor is not charged. And nothing is indicated in the question as well. So we are going to assume that the inductor was did not have any energy stored here. So the I naught should be equals to 0. And the question asks you to find the value of the expression for the current and the expression for the voltage across the capacitor. Okay, so let's do this. Right, again, this is a natural response. This is a natural response because there is no source in the circuit. And more importantly, we know that we have at least one element with some energy stored that is going to get discharged, in this case capacitor. Okay, now let's solve for the circuit, right? Well, the very first step always is finding out the initial conditions. We know that the initial condition of the capacitor is 100 volts provided in the circuit. So V naught is 100 volts, and the initial condition for the inductor I naught is 0 amperes. It did not have any energy, and nothing is provided in the circuit as well. So we are going to assume that the inductor had no energy at all. The second step, we have to find the Napier frequency and omega naught. So for a series RLC circuit, right, we found that the equation for the Napier frequency is R over 2L. The resistance is 560 ohms divided by 2 times 100 millihenry. Right, so 560 divided by 2 times 100 millihenry, it comes out to be 2800 radian per second, which is nice. Okay, so now let's find the value of omega naught. Omega naught is 1 over L, 1 over LC. So it's going to come out to be 1 over square root of, what is the square root of LC? L is 100 millihenry 10 to the minus 3 times capacitor 0.1 times micro 10 to the minus 6. It is going to come out to be 10 to the minus 4, 10 to the 4 radians, 10 to the 4 radians per second, and 10 to the 4 is 10,000, right? So from this we can see that my omega naught is greater than alpha, right? If my omega naught or omega naught square is greater than alpha square, the response should be my characteristic root equations will become the roots of the characteristic equation will become complex conjugate, and the solution will become underdamped, right? So it should be underdamped response. Okay, so once we determine the underdamped response, we have to write down the equation. Again, we can easily write down that equation from the table, right? From this table, once we find out underdamped, we need to pick this equation and then these two equations to find the constants. So the equation or the expression for the current comes out to be B1 e raised to power minus alpha t cos of omega dt plus B2 e raised to power minus alpha t again sine of omega dt. Again, this is greater or equals to 0. Okay, so this is the expression. In order to write this expression, I need to know the variables alpha, omega d, b1, and b2. I already know the value of the alpha, which is 2800 radians per second. What about omega d? I don't know. Let's find. Right? So the value of the omega d is, we know the expression, omega naught square minus alpha square. Omega naught is 10 to the 4 square, 10 to the 8 minus alpha square, 2800 square. So omega d comes out to be equals to 9600 radians. 9600 radians per second. Nice. Okay. So I got the value of the omega d now as well. And I already know the value of the alpha. So the only two things that are remaining are b1 and b2. We can find b1 and b2 again by solving this equation at I of 0 positive and di is 0 positive over dt, which we don't need to if we have the table available, because then I can just use these two equations right over here. So b1 equals to I naught, since our I naught is 0 ampere, so b1 becomes equals to 0. Nice. So this is gone. The second equation was minus alpha times b1 plus omega d b2 was equals to 1 over L minus R I naught minus V naught, right? So minus alpha is 20, so it doesn't matter, b1 is 0. So this is going to come out to be a big 0, plus omega d is 9600. 9600 b2 equals to 1 over L, which is 100 millihenry, minus R times I naught. I naught is again 0. It's going to make the whole thing 0. Minus V naught. Is it minus? Yeah, it's minus V naught. So this is going to come out to be minus 100. Okay. So then you can easily solve this thing for a value of B2, which should come out to be minus 0.1042 amperes. So you got a value of B1, 0, B2 this. If B1 is 0, your entire this term will go away and you're going to be left with only second term. So let's write down the expression of current. So the expression of the current is going to be B2. B2 is minus 0.1042 e raised to power minus alpha t. So alpha was 2800 radians per second t, and then we have sine of omega dt. What was omega d? Omega d was 9600. Okay, 9600 t, right? And this is in amperes. T is greater or equals to 0. So here's the expression for the value of the current. Now let's solve for the B part. Okay, so the B part asks you to find the capacitor voltage. Okay, sorry. Interestingly, we can find the value of the capacitor voltage. Again, we can easily use a series circuit. So your VR plus VC plus VR plus VC plus VL should be equals to 0. So you can easily find the value of the capacitor voltage equals minus R times I minus L di by dt. So what you can do is find a derivative of this equation and replace it back into this equation. So once you do that, because the value of the resistance is given and the value of the current is already over here. So all you need to do is to find the first derivative, and there are two t terms, right? So use a product rule. Find the derivative of the first term, keep the second term, and then keep the first term, find the derivative of the second term. Okay, so value of the capacitor voltage is going to come out to be 100 times cos of 9600 t plus 29.17 sine of 9600 t e raised to power minus alpha t, 2800 radians per second, right? So t, this is, so the unit is volts. And again, this is also t squared. So here's the capacitor voltage equation. Okay, again, very simple example. All you need is a table and very simple process. We have done this process a million times, if not a million times, so many times. Starting with the initial conditions, finding the values of alpha and omega naught, figuring out which one is greater, picking up a response, using that response as equation and figuring out what are the variables that you need to find. And if it is specific due to the render time response, then you need to find omega d, otherwise not, right? Otherwise, there will be only constants a1, a2, b1, b2, d1, d2, and for that a1, a2, two equations are given, b1, b2, two equations are given in those tables. So you can use those two equations to find the values and complete the expression. If those equations are not given, you can easily derive those equations by using this property. And we have derived those equations in the parallel RLC circuit examples in detail. Okay, so sounds good. So with that, I'm going to finish this kind of a short, quick thing. In the next part of the lecture, we are going to do the step response. And we just did a natural response, right? So only the step response, the final part is missing now. So we are going to complete that and then bye-bye. Okay, thank you. Good day.